After a very successful first symposium in Krakow, the second symposium is now hosted in Vienna. And as you can see, and probably have been seen, there is an interesting program, 26 sessions all in all, approximately 130 papers. Tomorrow there's also the Campus 21 workshop project in the morning, led by Carsten Menzel. The authorship is not only coming from Europe, but we do also have delegates from Australia, Chile, China, Japan, and the USA, and so that makes it really interesting as far as we can see. So it's also a good opportunity to see what is going on in the research area of building physics, what is being developed. Ardeshir Mahdavi will now deliver the opening address, Building Science with a Human Face.
As he mentioned, the first conference was organized by our colleagues in Poland, Dariusz Gavin and his team. It was a great conference, and I recall that at the beginning, Professor Heupel, who's also here, gave a very interesting talk about the traditions of building physics in Central Europe. He talked about various currents and various people. And I kind of want to continue that tradition, but since we are in Austria, focus a little bit on the background of at least one current of research and thinking, which is very, so to speak, germane to Austria. And my task is kind of simple because I don't have to talk about multiple people, but just one person. But that person is not me, just to set you at peace. But I do start with a small personal story. When I finished my first degree, I was fast at that time as opposed to current situation. And I came to Vienna, and my head was full of all kind of interest. I was interested in architecture, obviously. I was interested in physics, but I also kind of interested in music. And I couldn't decide what exactly I should do. And I met Professor Panshauser, who was one of the few, if not the only person, who did scientific work in the area of built environment in Technical University in Architecture. And he kind of tolerated for a certain amount of time me kind of following all kind of impulses. But at some point he suggested you might actually get a bit serious and focus a little bit. And he suggested that maybe I should focus on the area of room acoustics. Only later on I thought that was a very clever move on his part, because room acoustics is one of the areas of building physics which very creatively couples interests of in such diverse areas such as physics and music, performance, and obviously the architectural. And that's where I started, and if you want, never look back. In the last decades I have been working in this area, and very happily working in this area. If here and there, as it happens to you sometimes, you think maybe I should have done something else, I should confess, also in my case, sometimes, like for example, about 2 weeks ago, I and my team, we visited CERN in Switzerland. I had a little bit of a tingling of with this wonderful convergence of particle physics and cosmology that is right now ongoing. Maybe I should have pursued a real physics. No pun intended. Interestingly, the colleague who took us around was a Chinese-American particle physicist, and when we were talking, I asked a couple of questions, and then he looked at me and said, "Have you studied physics?" And I said, "Applied physics." He said, "Don't worry. Of the 3,000 people who were engaged in the Higgs boson research, about 200 were particle physicists, the rest were applied physicists." So all the stuff that you see was actually, so we are in good shape, so don't worry about that. Anyhow, but what do I mean when I talk about a specific school of building physics, if you want to call it the Austrian? Obviously, we are all building physicists, most of us, but we do very different things. You could say we do have different educational backgrounds. Some come from applied physics, some mechanical engineering, maybe civil engineering, material science, few from architecture. We are maybe interested in one or more domain, like heat transfer, illumination, or acoustics. Fire safety, recently even fields such as environmental impact assessment and so on and so forth. We might look at the buildings at very different scales, from microstructures of building materials over building elements and assemblies, all the way to whole buildings. And most of you are aware, one of the emerging areas of building physics in the last few years has been the urban physics, to deploy insights from the scientific inquiry in building physics in the urban level. And we have also different approaches. We sometimes very much focus, some of the colleagues, on very systematic laboratory-based research, for example, of building materials. Some do a lot of field studies, some are mostly occupied with computational studies and so on and so forth. Most of us use a combination of such approaches and follow case studies. Amongst all of these kind of sources of specific styles of building physics, there are also some other issues. Where we work, what is the level of construction culture where we work, what is the level of standardization, what is the level of professional education and practice, and what is the level of ecological environmental awareness in the respective countries and regions that we work. Those all have, so to speak, an impact and provide a kind of a signature of who are we professionally. But I think there's something more, and what I would like to do is maybe take the instance of Professor Erich Panshauser, for a long time was the chair of building physics in our university, and try to get a first approximation of what are specific features about this current of doing building physics. One issue is very important, is a continuous conversation between, so to speak, scientific inquiry and design thinking. As some of you might teach in architectural schools, you know of something like an almost eternal kind of conflict situation between architectural thinking and technical thinking. I happen to be, so to speak, in both worlds, and I notice sometimes how the different opinions in the respective communities are sometimes pretty derogatory and very critical. For example, in a lot of cases when you talk with architects, and I don't want to generalize that, but you hear things, references to building physics as being technocrats, and we have a kind of unkind word in German, Fachidiots, these are called, which means monodisciplinary idiots that just have very, kind of narrow field of view and so on and so forth. And what the building physicists think and say about architects, I don't need to talk about it in this community. We know all about all kinds of things that make us very angry when we look at public display of incompetence, for example, in designing a building. What I noticed in case of Panshauser was an approach towards the designers, to the planners, which was always kind of accompanied by respect. Very difficult architects who very seldom worked with people could work with architects. I have another colleague of us, our good architect Helmut Richter, is for me an interesting example. The reason that this very idiosyncratic architect could work with Panshauser was the fact that the Panshauser respect a specific capability of some architects do, and is to bring about from very different areas of requirements, human requirements, financial requirements, technical requirement, an integrated piece of artifact that would work. And by, so to speak, communicating that respect, he would also gain respect. And I think this is something that in our mutual professional communities has been missing. Another feature is this notion of integrated approach. We are scientists, and the scientists are very focused on specific issues, but the building production is inherently an integrated process involving multiple disciplines and multiple requirements. And that was something that he always focused on, and he always emphasized. He was engaged in the role of standards because he found that the standards could be a very nice mediators between high-level research findings and how the practitioners would have to translate those findings into real practice. As a result, he was always an active members of international European and Austrian standards and worked on those areas. Another issue which right now all of us talk about is the life cycle view, the integrated view over the building delivery process, beyond the operation phase all the way to the decommissioning of buildings. He represented and he propagated that idea some 40 years ago already in teaching and in research and so on. And last but not least, and that is maybe something that I would like to spend a few minutes on, is the central role of human beings and the human information processing, human perception, evaluation processes. That was something that would, let us say, provide a genius loci of the kind of building physics that was practiced in our school. Banshauser emerged from a tradition of what we call in German-speaking countries Hochbau, which is a building construction focus. German schools used, a German-speaking school used to be very good at this. It's not necessarily still always the case. They were very good. The fundamental understanding of how elements of buildings are put together was a central facet of education. And Banshauser came from that tradition. Karl Kupski was a very competent representative of tradition. But Banshauser also studied chemistry, which is this interesting juxtaposition of understanding the nuts and bolts of building construction, but have a scientific analytical view of how you go about understanding and research. So as a result, early 70s, he kind of saw, and I remember he saying that a real competent Hochbau is based on scientific understanding in building physics, because how a detail is put together is informed by the way how materials interact and how assemblies interact with the environment and the forces and things like that. So that was the way he approached that, plus a component that relates to the human factors, the human impact and role, which led him to establish his, so to speak, department as somewhat long in German, but a department which was based on building physics and human ecology foundations of building construction. Again, the concept is really quite, was ahead of its time some 40 years ago, and it took some time maybe for the rest of the community to understand. Purely professionally, I think it's really quite interesting to mention that after the oil shock of 1973, the Arab oil embargo, almost immediately after that, Banshauser, so to speak, got his hand on one of the first infrared thermography cameras. At that time, they were kind of bulky as opposed to today. And already 1974, he did a cross-section study of a large number of buildings in Austria, visualized the problem of unhindered heat transfer through the building envelope, and basically pontificated some 40 years ago fairly radical insulation thicknesses. And I remember that he was also later on, so to speak, in part criticized. A natural reaction was that he said, we can do an optimization. We can look at the factors pertaining to energy prices, estimations of energy price growth, and look at the embodied energy. And I don't say that we have to do these centimeters of insulation, but if you bring these objective factors into bear, then these rather substantial insulation thicknesses emerge out of that type of thinking. He was also one of the first, being first also is overrated, but I think he's one of the first people who introduced advanced computational method, in this case together with Walter Heindel, who was a mathematician, numeric, finite difference space calculations of thermal bridges, and early 80s, one of the first fairly comprehensive treatment of typical junctions and intersections as we could encounter, especially in massive construction styles in Austria. He then also pursued a number of studies in the areas of indoor air quality, natural ventilation, and a series of publications came from those areas that I will not spend time in detail. What I would like to spend a few times talk about this human ecology corner, because as die-hard building physicists, some of you, it might be maybe interesting for you, what was this angle? What was this introduction and how it came from? Panshauser met a biologist, Dr. Hermann Knoflacher, and I think the two of them had a very long and very fruitful interaction and collaboration. The most important idea was that if you think about the ultimate purpose of the building activity, it is about responding to human requirements. And the way as we approach the requirements of human beings as engineers and as scientists sometimes is rather, in absence of a better word, is sometimes deterministic. We sometimes treat people as if they are engineering systems, and if we know something about input and output, we can predict everything about them, classify them, and then get on with the rest of the deal. And it seemed that this was a problem, and it still is a problem, and the idea of incorporating human ecology in teaching, in education, addressed that. In order to kind of demonstrate that a little bit, I just mentioned two pair of concepts from human ecology without going in a lot into the details of it, where Knoflacher and Panshauser introduced already to the undergraduate students. One notion was if you want, a contrast between the human potency of living beings. You talk about human being, but I take a sheep as an example, is just do as well. And the ecological valency of the surrounding environment. The idea was that we, equipped with a certain genetic and physiological background, have certain possibilities in perception, in action, in motoric, in cognition. And we are, so to speak, confronted with a surrounding world which provides us with certain potential, be that food or amenities or shelter or sexual partners or whatever. And from this purely biological point of view, you could say that what we should be talking about is not the individual living beings and not the surrounding world, but the interaction of the two. And that was, so to speak, the insight of human ecology, that a lot of problems that we discuss rise in that interface. To make an example, today we talk about universal design, design for all, as a discipline in which it's postulated that the design should not be based on a normal, so to speak, average, healthy, and young human being. That the so-called ecological potency of people as they go through life and day by day is continuously changing. If architects and engineers hard, so to speak, wire buildings into a notion of a so to speak, user that is very standard, then you got a large spectrum of people who will not actually find that environment suitable. Just to give you an example, Professor Knoflacher, who will provide the keynote today, used to ask his students to sit in wheelchairs for fairly long amount of time. He's a professor in traffic systems, in order for these students to understand what does it mean if you have to work and move in an environment which is not designed for your ecological potency. So the idea of something like that, that today is for us fairly evident, was 40 years ago quite a important move. A second concept, a pair of concepts which I would quote from the human ecology, is the notion of environmental relationships, those relationships that I talked about. Panshauser and Knoflacher suggested that we can associate with our relationship with our surrounding world two aspects. One is the physically relevant one, energy transfer. We see photons of light and we have light perception, or we are exposed to infrared radiation and our sensors kind of receive and process that information. But the other aspect is the meaning of certain signals and the patterns that we receive, and those information-related aspects also affects our perception and evaluation of the built environment. This is also interesting because, as I mentioned, as engineers, in many cases we like to make things simple, and we say if we have an environmental exposure situation, for example, noise levels, or let's say temperature levels, it would be very nice if we would have a prediction tool that almost deterministically say, you subject to people to certain conditions, you should expect some percentage of them being dissatisfied or uncomfortable or something like that. You know, most of our visual comfort, thermal comfort standards are originally based on this type of thinking. Now the problem is that this one-sided interaction between energetically, so to speak, limited factors and people's perception simply does not apply. I would like to maybe underline that with an example, again from the human ecology colleague Haider, who was in the area of medicine and hygiene, did a beautiful experiment which I many years ago repeated at Carnegie Mellon and got pretty much the same results. What he did, he exposed a large number of people in a lecture room to noise, to a sound exposure, and asked them to evaluate that on a semantic differential. As you see here in the left side are kind of negative attributes, and on the right side are kind of positive attributes. Psychologists use this type of semantic differential to understand how people evaluate something. The noise that he exposed these people were introduced at two different levels of intensity. One was at 90 decibel, you see the red line, and the other one was at 70 decibel, which is the blue line. And as you see, and you would expect, the somewhat softer sometimes is somewhat more positively evaluated as the louder exposure. But he did something else which I found very interesting. He did a second experiment, and in that experiment, again, people were exposed to a noise exposure, but in one case, it was told that this is a waterfall, and in the other case, it was told that it was a factory noise. And as you see, it was a huge evaluation difference. Now, the nice thing is about this experiment was that the exposure was exactly the same thing. It was basically white noise. And as building physicists, you know white noise can sound like a waterfall. It also can sound like a factory. The sound level was exactly the same. So that means the discrepancy that you get from this exposure is purely based on people's attitudes towards the suspected source of exposure and not any real physical issue. Now, this has been again and again displayed, and I suspect that today when we talk about thermal comfort standards, as many of you know, it has been shown that there is a difference in perception of the thermal comfort situation if a building is naturally ventilated or if it's mechanically run. We know now that in free-running buildings where there is no natural ventilation, the classical Fanga comfort model does not perform that well. And I submit to you that part of it has to do with the attitudes. A number of colleagues, Didier, Bordas, and so on, have shown that even such things like if the occupants believe they are in a green building or not affects the level of tolerance for the thermal conditions in the buildings and their evaluations. Again, this is something, and I think that is what was achievements, if you want, of the Austrian school, that these issues were talked about and it was dealt with in a continuous basis. My own research is affected a little bit, part of it, for example, trying to understand people's behavior in building. Most of the time in simulation studies, we have a very rigid view of how we simulate people coming into the building, going out of the building, and behavior. If you observe real buildings, you see that these aggregate models really do not apply. If you move into individual buildings and individual offices and individual days, you see there is a huge variance, even by the same individual, in terms of how people interact with the systems. And in order to understand that, the ecological potency of these people have to be considered. Even in the long term, those behavioral issues are important. One example, one of our PhD students, Mr. Hus, and Mr. Pont will present a paper on this subject, studied a number of retrofit projects in Austria where the people were, where these buildings were updated, retrofitted to the passive house standard. And he looked at the performance of this building before and after the retrofit. And here you see the estimated heat demand of these buildings according to the projections of the energy certificate before the retrofit. Heating demand in kilowatt hours per square per meter. And here is the actual heating demand after the retrofit in the operation. And in order to understand that, for example, there was a number of hypotheses. If you attend that paper, you will see that. But we think that human behavior, the fact that in these buildings, accounting for the energy cost was not done at the individual level, but for the entire buildings, based on square meter level, led to the displayed interest in doing a lot of ventilation in winter. So when you adjusted for the ventilation behavior, you could see that the prediction, matching between the projected and the actual demand actually fits better. So that displays to me the importance of this human factor. There's one last thing before I conclude that I would like to maybe mention, but this is a most difficult concept, and I was thinking even yesterday how I should communicate to you that rather intangible experience of working in this school and working with Panshauser is actually transcends a little bit of building physics. And I take you back to CERN, and I thought maybe the only way I can provide some glimpse of what I'm trying to say is mention an experience. As I mentioned to you 2 weeks ago, we had visiting this facility, and I was talking to this colleague, to this physicist, and of course there are a number of things that you know about CERN. You know, there's 27 kilometers basically tunnel. There are protons that are accelerated almost to the speed of light. 9,300 magnets, 40 tons of metal, which is, in order to achieve superconductivity, is brought from room temperature to almost 0 degree Kelvin. Think about the energies. 120 megawatt power required, which is equal to almost all homes of the Swiss canton of Genoa. So I was talking to this person. I was interested. You're a building physicist. You're always a building physicist. I said, what are you guys doing with this reject heat? And it was interesting. Applied physicist asking a particular physicist. He said, I think we just eject it into the atmosphere. Anyhow, so you look at this cost, 4.7 billions, Large Hadron Collider construction cost, annual operation $1 billion, and all annual CERN expenses 5.5. Anyhow, when we came out of that, a colleague, building simulation specialist, came to me and said, it's very important what you said. It shows how stupid our investments are, and we need all these things and so on and so forth. And I said, no, my friend, that was not what I was getting at. I would support the CERN research. And I said, why? I said, if you are worried in a global sense about our investments, what about this? 2011, US and the next 13 countries, military investments. $711 billion 2011, just United States of America. And another such sum from the next 13 countries. If you want to talk about efficient investments, I'm with you. But you start there. Cut 1% of that, and you're gonna support the operation of CERN. Because at the end of the day, you're engineers, you're scientists, but you're also citizens of a society. And I ask you, if there would be an alien invention, let's say, and we would be asked, what has the human race achieved? What have you guys done? These questions have been asked of people. Some people say, I don't know, the last 3 string quartets of Beethoven, or Last Supper, or Sistine Chapel, or so. I would say CERN. I would say we people, with all our wars and all our problems, we try to understand the world. We try to understand where we come from. And that speaks for us. And this type of thinking of getting, so to speak, not bogged down in one specific view of issue, but obtaining information from multiple resources was something that I learned from Panshauser. He always quoted Professor Reichhardt, who said, citizens of a society have a moral duty to obtain information, to inform themselves towards making decisions and towards acting in their role as an agent of a change in the society. So, ladies and gentlemen, Professor Panzhauser is not a man of big gestures and big words, but I did want to mention he has turned this year 80 years. He has provided 50 years of service and leadership in communication of building physics in Austria and beyond. And I wanted to personally tell him that we are, my team, my colleagues, my friends, and all of your colleagues, thankful that your service. Thank you, Harish.
We are proceeding now with our keynote speaker. Professor Hermann Knoflacher has a similar triangle in his education, maybe not so wide, but still there is civil engineering, there's geodesy, and mathematics as completed degrees. Nearly 4 decades ago, he set up here the Institute for Transport Planning, which has been a very renowned and successful institute. And well, as I said in the beginning, we hope that you will not immediately proceed into the Kärntnerstraße, which is close here. Also, this street has been a street where a long time traffic was along. Nowadays, you will find here a very nice pedestrian zone, which does also function if the shops are not in operation. People are there. You would say it's a kind of promenade. And the city of Vienna has so to say, a second location, which was for some time discovered is in that direction, the Marilferstraße, which is also expected to become a pedestrian zone. It's under construction, as you can see. Go there by yourself and see how, so to say, several parties are negotiating with each other. Professor Knoflacher is also known for his excessive criticism of automobile usage, you would say in German, sometimes a bit unüblich, uncommon, but that is what we need in this area.
A faculty is a kind of desert, in principle, for people who are changing the paradigm. And then we are looking around, where can you find a oasis? And my colleague Panzhauser was one of the few oases in the Technical University. Here you can find people who have a similar kind of thinking. I was encouraged to skip my presentation and to make a lecture here on the board because Mahdavi has shown a wonderful development of kind of paradigm change also in the architecture and urban planning, which is rather similar to what happened in. This is going on. I can. Oh, wonderful! Thank you. So, you have the written contribution, which I was asked to prepare. So I don't follow the written contribution because this gives no added value. I show you just into the city situation, because it is very often forgotten that the city precondition is a society which agree with each other. If this wouldn't happen, the people wouldn't be able to build cities. And it is very interesting that this artificial body must be an expression of the human values, human culture, and so on, and the feedback too. So the traditional city view looks like this one. It is a very compact city. This is the typical historical city. You don't easily recognize a certain order. We have discovered later on a very clear order within this, I would say, chaotic kind of cities, which architects don't like, because architects have straight linears and straight tools, and they use it, and they develop different cities. It is very interesting that the patterns of the city worldwide are more or less similar if you have learned to look to the city and you have discovered what is going on. Because the core of human settlement was not the street, the core was always a place. And this has been forgotten so far in the architecture and urban planning today. And it's very interesting that we discovered, together with a very genius architect, it was Professor Reiner. He had I would say, a subconscious feeling of the city life. This was very interesting for me, and I had the opportunity to work with him for many years. This was Vienna, this is London, but you can take any city of the globe. This is Delhi, city center, the walled city. You find everywhere the same kind of patterns, although the city is totally different looking. This is very interesting. And this vitality of the city is depending on the fine arteries of pedestrian networks. And my experience is when I was able to pedestrianize several cities in Europe and other places, the people recognized, well, there's something missing. And what they happened in the historical city parts, they recognized, well, we need some pedestrian through paths. And then discovered the old through walks. And they opened it. This is a very interesting situation. It is like a healing body. So the problem is the cities are coming out of our brain. This is where the human cities here, and they have this kind of view. It looks nice. I think everybody have a good feeling if he can live and work in such environment. Data, behavior, and structures is very interesting, are not very well known in its relationship in the different disciplines. They are changing structures because the think structures are something different than behavior, and we have some data, and everything seems clear. But the problem is that this kind of relationships are not linear, as it has been mentioned already. So we have our longest experience is the experience with the nature. We have the behavior of nature, we have the data of the nature as much as we can perceive, and we have the individuals or the group's behavior. But behind of them are the structures. This is the body structure, of course, and the human structure, and we have the structures in the environment. And they are connected to each other. And over the time, the people were able to adapt to the needs of the nature because they couldn't change the nature substantially. If they make the mistakes, well, they have to adapt because the nature hit back immediately because the interference was also direct. Today, we interfere into the nature, not directly anymore, and we have some time delays which can create a lot of problems. So what is happening when people were able to gather together, they developed a social system, they developed their own environment. And their own environment is their own structure. They think it should be working and will be beneficial for them. And finally, they were able to create a city. This is exactly nothing else than urban development. They developed their environment over time, over a period, at least as we know about, of 10,000 years. This was the city, and we have still very nice kind of cities where they attract the people, like Venice. You can study in Venice, I would say, the internal mechanism of human urban cities, or this kind of structure everywhere, or this kind of business structures in the cities, a lot of shops. I have analyzed the situation in Delhi, and it's very interesting that the turnover per square meter is more or less the same like in our big shopping centers. Even the income is much, about 1/50 of what we have here. A very interesting thing. I totally underestimated the number of shops. I thought I can make a complete survey, and they told me, well, there are at least more than 100,000 shops in this small part of the city, and about up to 500 people per hectare, which is also the case in Vienna. 5th district of Vienna had 500 people per hectare also living there. And this is really what is the real market. We are using the term market today toward things which has nothing to do with the market. This is the real market. Today we have plastic bags with the lowest level of quality here with the highest price in our shops, and we cannot choose it before we buy it. Here I can test and use the market. So the secret behind this is the transport system of the past. The only transport system, we are able to use it in a responsible way. This is walking. And the walking speed is low, the distance we can cover is also low. And everything we need, we have to arrange within the walking speed, distance. We cannot go out. So we have to arrange with other people, even with people that we don't like. And this brings progress to the society. This is social development. As soon as we can escape, we only choose people we like. Then we create the social problems of today. Well, this is very much to do that we are not haven't been very successful in physical mobility. Our speed is very low. Sensual ability is also not very high for high speeds, but we have a certain part in our body which developed rather fast. This is the neocortex. When in the last 10 million of years, the neocortex developed very fast, and this provided us with mental mobility. This mental mobility is the success story of humans, not the physical mobility. But the mental mobility can make a lot of mistakes, like in our transport system. So if we look to the situation over the experience of mankind, it is about 6 to 8 million of years walking in the upright position. We were always walking all the time. Then we discovered the coal and steam engine, the oil combustion engine, and then we were always walking. And suddenly, in the last 200 years, the situation changed. Because today this is not a normal speed. People are talking about 30 kilometers is too low. I remember in the 70s, a famous motor journalist told me, he was a very fat man, about 160 kilos of body weight, and he said to me, "Oh, you are totally crazy with 30 kilometers. Nobody can drive with 30 kilometers." And I told him, "Well, please run to the next corner with 30 kilometers and come back." And then we were talking whether it was fast or slow. And then he stopped his attacks against me. So this has changed the situation totally, and this was too much for professional disciplines in the political arena, in the professional world, and in the society. This is a totally unnormal situation. And what have engineers done? They have provided this because the people were extremely happy with the high speeds. And this seemed to be, for the youngsters here, the absolute normal situation. This is absolutely unnormal situation. And since the engineers didn't know, well, they had made some experiments, and they said, "Oh, these experiments works very nice. The people were happy, the politicians were happy. They got their professional progress, and they created the pillars of traditional transport planning. And these pillars of traditional transport planning are based on growth of mobility. Probably most of you believe it because you read it in the newspaper. Then they believe on time saving by increasing speed, because everybody of you have the experience that you can save time if you drive faster. And everybody of you are happy if you can choose between different modes. So the more modes we have, the more freedom of choice we have. This was the basis of my education, and is still the basis of the education, I would say, of most of the universities. So then this would be a nice story to tell you why I came to this kind of crazy thinking. Because the observation and empirical evidence is very easy. People buy cars, so they are becoming mobile. Increasing mobility is absolutely true. So people without cars are not mobile at all. So if you look to, they are like plants. If you look to your ancestors, you will find them like trees or plants or something like that. But this is not the case. People have been mobile before. It is interesting, why are people going out of the house? We have seen these nice diagrams where the people are in the house, and what is the problem is if they are going out of the house. Why are people going out of the house? Because something is needed. They have no working place there, they have nothing to eat, they have no education there, and so on. So the cause of each physical movement is the problem and the demand on the spot which you have to leave. And you hope to find the satisfaction at the destination. This is the cause of physical mobility. If you are happy and everything is wonderful around you, you are in a kind of paradise, you don't have to move very much. And if you go back to the Bible, you find the solution. The people went off of the balance of the environment, okay, then they had to go out of the paradise. And today it is very attractive to go out of the paradise because we have the cars. So each trip is connected with a purpose. And if you fulfill the purpose with the car, you cannot fulfill it at the same time as a pedestrian, cyclist, or public transport users. It is eaten up by the car traffic. And what is happening here, really, number of purposes is constant. And what is happening here, number of trips with pedestrians, cyclists, and public transport has decreased with the same amount as the car mobility has increased. So a purposeless mobility can grow. A purposeful mobility cannot grow. because the average number of trips is absolutely constant. We know it since 30 years with many empirical data. Before, with the normal service, we get about 3.2 or 2.8 trips per person per day. Today, with the GPS system, we know it is about 4 trips per day in the average. Younger people make less trips when they are children outside of the home. Then they have the problems with the hormones and the business and so on. They have maximum trips. And when they're becoming older, well, they stay much more at home. This is the situation. If somebody is talking about growth of mobility, he's totally mad. He is really a dangerous, mad person. Because mobility is constant. We can only change the kind of mobility, but we cannot change the number of trips in the society. Well, you can change the number of trips in the society. If you destroy the environment, everybody has to flee to go somewhere else. This is the problem. So the question is, we have to save time. To save time, we are building wonderful things like these motorways. This is the city center of Shanghai. They have removed about 2 million of people to save time, of course. And the calculation is very simple. We have 2 points A and B, and then we connect them with a fast transport system with a higher speed, speed 2, and then we calculate it by this very simple formula, and this gives the benefits, and then we calculate the investments, and if the investments and costs are less than this kind of benefits coming out of this really physical miracle of saving time. You can save time. In physics, you cannot save time, but in transport, we can do it. And the economists are calculating it, and this is the big benefit. And if this more than 1 or 3, whatever it is, then we invest. And then we create a very big deficit over time, as you know. Well, if we look to the empirical data, I show you one of the studies from MIT and EASA from Schaffer. Here on the horizontal axis, you see the annual income on the left side, and vertically, this is the travel time budget, all the trips during one day. And you see if the people on the left side, which have no money, they have no cars, we have 500 and even more cars per 1,000 inhabitants. On the left side, the people are walking. We are driving very fast and very convenient. We would expect the travel time budget from our calculations, which look like this one. So people are slow, they need more time. Societies who are fast can save a lot of time. But this is not the case. Globally, travel time is constant. This is very interesting, so we cannot save time. What is happening in this case, travel time budget is the same. This I know from my analysis. This is the travel time for each of the single trip. And this is the distribution for, you see on the left side, here the pedestrians. And pedestrians walk in the city with an average speed of 3 kilometers an hour, and car drivers drive with about 17 kilometers an hour. And if the faster would save time, they must be on the left side of the pedestrians. This is not the case. This is the travel time distribution of car users. They cannot save time. It is very simple what must happen. If travel time is constant, speed goes up, well, distance is going up. So if you increase the distance, the speed, you must increase the distance. And what is happening? On each end of each trip, there is an opportunity. And if you increase the speed, the opportunity goes away. And this creates, if you overlap it with the economy of scale principles and so on, then you know, well, you kill all small shops, all local opportunities, and you create a big playing field for big corporations. Power of corporation is based on this effect. If they wouldn't have the high-speed systems, they couldn't grow. Very interesting situation. So what is happening to the city? City is developed or has changed into an agglomeration. Urban sprawl for housing and concentrated economic activities and administrative activities. So it is totally separated. But the city, it's up a lot of, this is the situations here. Urban planners make these very nice designs for housing things. This is close to Washington, and you have no opportunity for pedestrians for shopping anymore. If somebody has no car, he had to do a long walk to find something to buy. Well, going back to the system behavior, this is the real system behavior. There is nil by increasing speed, time saving. And you can multiply whatever you want with nil. It is always nil. They're just creating problems. So speed has no value anymore in general. Some certain cases, but not in general. So this is the situation, but what is happening? Well, these kind of structures need a lot of energy for mobility to keep them together. This is the problem. This body can only exist as a city as long as you have an input of energy. It is like in emergency, a man or somebody in the emergency room in the hospital, as long as you fill in the life blood of this kind of cities, which is in this case fossil fuel, they will exist. This is the situation, and if you want to go to a sustainable kind of cities, we have to go down. We have been living here all the time, and we are up here. You see the top cities, they are in the United States, then you have the American, then you have the Australian, the European, then you have the Asian cities here. This is Bangkok. Bangkok, for example, has to go down. Well, this is a very simple, we make a short mathematical exercise. This is a basic formula. This is the amount of anything. Let me say flow of water through a tube. This is the cross-section, and this is the speed. So this is a very simple situation here. But we have to take a little bit about, this is a basic equation of any kind of mobility and its effects. Very simple to calculate. If we had, before we had the constraints. We didn't have, for example, transport energy enough, and we had not the high speed, because the speed was the speed of the pedestrians. Energy was solar energy for humans and the animals, whatever, water and something like that. To build a city, it was necessary to increase the density. This was the cause why the people had to join the others and to build a social system, because they couldn't escape. This was the secret, the very simple formula. So the density had to go up under these circumstances. This is very much important. And this creates the intelligent city, because the intelligent has to build into the structure. If you have a total stupid structure, ITS, be careful. I will show you later on. So this is the really intelligent city. This is the historical city, because it is sustainable, needs not so much energy, and so on. So the secret of the urban damage, we have now a lot of energy, and we have great speed. So we can escape from the burdens of the society and other burdens. We can make very short-term, cheap investments somewhere else. We can find wonderful places to live and so on. So the density is going up. Very easy to explain. So what is happening here? This is creating the urban problem. The engineers in my field are learning this kind of formula. This is the traffic flow in cars. Normally this is the density, cars per kilometer, and this is the speed in kilometers per hour. And if the speed is not satisfactory, and we have congestion, what are the engineers doing? Build more lanes to reduce the density. So density goes down. Wonderful. And they are happy because the speed is now going up, because they believe, well, first of all, but if the density is going up, car use is much more attractive. More people go in the system of cars. Okay? And if the speed is also increasing, which makes the engineers happy because they believe on time saving, well, in the system, the speed is also enhancing a little bit. So, and finally, they are creating a wonderful congestion. This is traditional transport planning. This is the therapy, how traditional transport planners treat transport systems and cities. So they are maximizing congestion, of course, and air pollution and all the other things. Very simple, because they don't recognize the system effects. They are only taking into account the cross-section view. But the system is not a cross-section view. So what they are happening, they are also ignoring the system behavior. These are the common formula to calculate traffic demand. This is the potential or the population in the one city and the population in the other city. And this is the resistance factor, money, terms, distance, and whatever it is, travel time. And they are introducing here some counting stations, and if the counting stations show, well, there is an increase of more cars, then we have to fulfill the need of these cars, so we have to reduce the resistance. We build a nice new road. This is the traditional decision procedure. And what is happening, of course, then they are happy. Well, our forecast was absolutely proper and correct because we have now much more traffic. But they don't know how mobility functions because the trips outside are missing inside, because the number of trips is in the system a constant. So all the trips, the engineers are happy to count them outside, are missing destinations in the inner structure of the body of the city. If you would go to a hospital and the medical doctor would recognize, well, we have a big pressure in your arteries, I think we must open them because there is a lot of molecules there, they want to go out to the center of the globe. I think you wouldn't survive. You're running out like the cities are running out by this kind of treatment. And you destroy the basic life of the cities here. So they are losing. And since the car came into use, the people didn't build any more cities for people. They built cities for cars. This is the urban planning since 200 years at least, or last 100 years. And this is the effect. And now we are coming to the ITS system. The definition of ITS is this: information and communication technologies in the field of road transport, including infrastructure, vehicles, and so on, traffic management, and so on. And this is European ITS approach. There is nothing said about cities, nothing said about life and something like that. This is exactly what the companies producing electronics wish. They want to equip the situation with electronics. But the problem is parking. Because at the origins and destinations, everything is full of cars. This is a very highly developed parking situation. And this is exactly what is happening. But if we do what the shop owners like to have parking places everywhere. And if you fulfill the wishes of the shop owners, you destroy the city. You see it here. There are very nice analysis from my colleagues in Japan. They have found that the more car parks are, the less shops are there. Of course, because nobody leaves the money in the car. And this hasn't been recognized. It is the immediately the close relation between man and car. And the building standards force the people to provide a place for parking for cars. And urban planners allow this situation. In the 70s, I discovered a very interesting relationship. I didn't know this kind of relationship between distance to the feeding place and the frequency of waggle dances from the bees. From Karl von Frisch, he discovered in the 40s of the last century the language of bees. And the bees inform the other bees at home how far they have to fly. And this is by waggle dances, and the frequency of the waggle dances show you exactly how far they have to fly to find the next gasoline or feeding station. And some researcher in Germany published a study where he analyzed the situation of people's estimating walking time in relation to travel time. And we repeated this kind of study in Vienna with another method. And this is the relationship. I think this is the pointer. Is there a pointer here? Yes. Yeah. In the middle. Here. Oh yeah. This is the walking distance, and this is the acceptance of walking of pedestrians of a public transport stop in Vienna. And you see in a car-oriented environment, the Viennese accept the public transport stop by about 100%, and then it is decreased with the same mathematical formula. And this formula is very interesting because it represents a very old law. It is a Weber-Fechner's irritation law, and the cause of this situation was energy. In both cases, body energy creates this kind of behavior. And this is very interesting. If we go back to our evolutionary development, we are starting here from the atoms, molecules, and so on to our technical society. The car is a product of our technical society, it comes out here, but it changed our behavior on this level because it slips very deep in the core of our brain. And from this point out, it changed everything towards the car. I will show you, because I'm sure each of you is totally infected with the car virus. You have not recognized it so far. And this caused the effects, and it changed everything, the values, the structure, and the culture from inward. You don't recognize it, because the car tells you what you have to see. So in the planner's brain, now the man is replaced by the car, because planners think and build and deal with cars, of course. They create apartments with parking. They create carriageways instead of a nice living environment for people. And if the people are not doing this, they have to pay for it. They are punished. They are forced to build life space for cars. These are typical planning regulations. This is the virus and the effect of cars. And the people don't see it because the people are happy because they have the brain in the car, and the car in the brain tell them, oh, wonderful what you have done. So it is very interesting to look what is the basis of this law. It is the Reichsgaragenordnung from 1939. And this has this kind of paragraph 2, and this paragraph 2 is everywhere included in the German, Swiss, Austrian, French, and everywhere. Building standards. This is the building standards which force the people to be infected with a car. A wonderful, wonderful situation for this situation. So at the origin we have the people and destination also, and the informations and the value system is created by this one. And cars are parked everywhere at the origin, at destination, and in between you have a wonderful environment for cars and not a wonderful environment for walk, cycle, or whatever. What are people doing? Of course, they are intelligent and selfish. They use the cars because they are forced to use the cars. So we make now the test. Is anything strange for you here in this picture? No, I think you are familiar with this. You think this is normal, yeah? Okay. No, I see, yeah. Nobody is claiming about this situation. Huh? Now I am appearing in a different way. Would you accept that everybody would walk around with this frame, the so-called walking tool? Would you think if everybody is walking around and there's some problems, you would invest billions to make it easier to walk in this way? Break down this building that everybody can go in and park his walking tools in front of this room? Oh, what is the difference? This is the upright walking position you expect from an upright walking human or an animal or a human cultural behavior. But if I am sitting in the car, you are also sitting in the car, and you think like a car would like that you should think and see the world. You don't see the world anymore. This is the reason why all my students since 35 years have to make the experiences with a wheelchair drive, and I can recommend it to you also. Do it. 1 hour, then you know what we have built so far. Well, you see, it is a wonderful thing. It is a cabriolet. And if the weather is nice, as it was at this time, I can quickly move through the city. I have the only problem. I am stuck in the congestion. And now you are all intelligent people. You know now that the car virus is controlling your view to the outside world. And within 1 second, please answer what is wrong in this picture. Emotionally, you will say, this crazy guy with the frame. Because the car say, well, this is absolutely normal, not normal. But everything around me is absolutely abnormal if you remove the car from out of your brain. I know it is a pain. Otherwise, you cannot work on urban planning as long as you have your brain controlled by the car. Just to give you a short hint of because this is a positive feedback. exponential positive feedback. A very bad situation. I am now searching for a parking place. So I have got now my parking place, and this is our parking problem. Finally, we leave it here. Normally with 5 seats, and say, oh, this is a problem, we must make more parking places, and so on. Do you see any wallet here? No, you shouldn't leave your wallet in the parked cars, but the shop owners think, oh, each car is full with wallets, and the money flows in my shop. This is my daily business in practical work. Okay, and this is a practical experience. Well, it is used now worldwide. You can download it from our webpage. So the urban physics of ignorance looks like this one. You have the cars at home. If you have the cars at home, you can make absolute stupid urban planning, because you can separate working, shopping, and everything, and have to provide just parking there, nothing else. And you destroy, of course, the city. You don't need people around you. You need just a parking place. Today, well, it is better to have a computer maybe instead of people. And public transport, this is acceptance function of public transport. And you have a damage of public space. Okay, this is one of the problems we have today. So this is the way, this is physics. Walking distance is, of course, physics. And if you park the car here, it's also physics. This is building physics, of course, because you decide how the people will behave later on if you provide a parking place at home, because you change or transfer humans into car users and to destroy the city. It is not the transport engineers. They are just dealing with the symptoms. Traffic flows. Traffic flow is just a symptom. If I change the parking organization, all the traffic flows are disappearing. You will recognize Vienna is not a city with a high congestion level. We have a very low congestion level. The reason is we start to control parking. And people are walking much farther if there is no car environment. This is also very interesting, because about 220 meters is the average distance between places in historical cities, everywhere, globally. This is the real, I would say, healthy pattern of a city. And this is the public transport stop, and you see what is happening. We destroy public transport, of course, and we destroy the local environment. Because the problem is the car with about 240 horsepower, something like that, slip into our legs and go into our brain. But the neocortex is not strong enough to control it, and this creates the problem. The evolutionary situation was too fast for us. Maybe in 20 billion of years we will be able to control mentally the car. So parking regulation is the problem. And ITS, which is dealing mainly with traffic flows, don't understand the real system behavior. This is the problem. This is also the same situation if you would equip, let me say, the lion or the tiger with additional ITS systems and want to save the environment and the other animals. We are putting the ITS system to the most aggressive partner in the transport system, to the cars, and this is the absolutely mistake. ITS shouldn't be implemented there. We have to change the physical structure, then it is much easier. Well, it's very easy for you as physics, what is at minimum necessary. At minimum, it is necessary to have equidistance to public transport if we want to give the people a chance of choice. We have to introduce a situation where the people have at least the same walking distance to the public transport as to their parked cars, and in the opposite situation the same. Or this would be a more elegant situation, put the cars on the other side, and on this side you have the living city, on the other side you have whatever you want. Then the people get rid of cars by themselves. You don't need to fight against the cars. This is then the life space for business and the city, and these are the empirical data. Well, you see, it is not a very strict relationship, but it is absolutely representing what is happening here in the theory, because it is not only distance, it is also the quality of environment, and so on, and so on, and so on. But the gravity law is also not visible everywhere. If you look to the wind effects and something else, you will see, well, the gravity law is represented in a very different way. But this is the basic law, how the system and the people behave. We can simulate the situation, and we can check it in empirical data. If we take this situation as normal as we have it today with 100%, if we change the situation from today, where the people have the cars at home, to a situation where the garages are 1 kilometer away and the public transport stops are 500 meters away, and take into account the behavior of pedestrians, cyclists, and public transport, only about 3% of people will use their cars. Because the environment tells them, well, it's much better to have an alternative mode. This is the situation, and it works also in cities, of course. In Vienna, we have introduced the master plan in 75, then we have changed a little bit the structures over time, and since 2002, we have a decrease of car ownership, not only car use. We have a decrease of car ownership in Vienna every year, continuously since this time, because the structures, physical structures, have changed. First of all, and secondly, we have now an increase of public transport modal share from about 29 to 40% in the last 15 years. And at the same time, we have a decrease for car trips of the same amount, about 39 to 27%. So we can change the structure. It is the physical structure we have to change. And I think this is also a responsibility of building physics, not only thermal, because you don't like to release heat out of the building, but you release the people out of the building if you make this kind of physics or physical structure. Because if you provide the people with parking places, then you release them out of the city. So this was the old paradigm. We have I am finishing, and this is the new paradigm. Of course, there is no growth of mobility in the transport system. There is no time saving on the system level. As an individual, you will always save time if you move faster. But you will change, if all the people are moving faster, the structure in which you live. And the real behavior of the people is depending on the structures you provide for them. We can change the situation. Well, if you are interested to read something in German, unfortunately, well, there are a lot of English publications too. And you see this is a total not mobile being, but it's nice, isn't it? And makes you happy. Thank you.